Hello class, today we'll be looking at glaciers and glaciation. So glaciers are part of two fundamental cycles within the Earth systems, the hydrosphere and the geosphere. So as we saw in chapters 13 and 14, in the hydrologic cycle, water will be evapotranspirated into the atmosphere. Once there is an accumulation of this moisture in the atmosphere, there is precipitation. Some of this precipitation falls in the oceans, some of it will fall on land. The one that falls on land can either infiltrate, it can percolate, it can flow as runoff, or if it falls at high elevations or latitudes, the water may be stored as solid water, either as snow or as ice. Sometimes, if this said precipitation happens at an existing glacier location, or if the conditions are just right so that the snow that falls can itself start forming a glacier, then that water can be stored for many, many years, sometimes centuries or even thousands of years, before it eventually infiltrates or percolates or becomes runoff to eventually flow back into the ocean. So glaciers make a big part of the hydrosphere, make a big impact in the hydrologic cycle. So a glacier itself will be a thick mass of ice that forms over hundreds or thousands of years. Glaciers originate on land from the accumulation, compaction, and recrystallization of snow. Glaciers appear to us motionless, but they do in fact move. They move slowly, but they move. And like many of the other agents that we have seen thus far in the class, namely water and wind, glaciers can erode, they can transport, and they can deposit sediment as they move. Because of this property, glaciers are also basic in the need for the rock cycle. They're big erosional agents, depositional ones, and transport ones as well. And although glaciers can typically be found in many parts of the world, they are mostly located in areas that are relatively remote, either near the Earth's poles or in very high elevations, high mountains. So there are two main types of glaciers. There are valley glaciers and there are ice sheets. And these two are also kind of subdivided, or there are other glaciers that kind of branch out from these. So valley glaciers, which are also called alpine glaciers, are glaciers that form in mountainous areas. They typically occupy valleys that were originally occupied by a stream or by a lake. Some of the glacier locations can be all the way up to the ridge part of the mountain, or they could all be all the way down in the main outflow valley, or they could be connected as well. Unlike the rivers that would have once occupied these areas, however, the speed of the glacier's movement can be only perhaps a few centimeters a day, or even much, much slower than that. Each glacier itself will behave relatively similar to a stream, because it really is a stream. It's made out of ice, but it is still a stream. So this stream of ice is confined by rock walls on the sides, and it will flow down the valley from an accumulation center near the head of the glacier, which is up above. And just like rivers, valley glaciers can have different arrangements. They can be long or they can be short, they can be wide or they can be narrow. And they also, as I said before, can be connected to other tributary glaciers, or they can be completely separate from them, like you're seeing in this picture. So you're seeing this glacier over here, not connected. So they're most often found to be more long than they are wide, and they are isolated from other glaciers for the most part on the other side of a rock wall, like you saw in the picture. And these valley glaciers are also typically found in high elevation areas, such as the Alps in Europe, which is why they are also called alpine glaciers, after the Alps in Europe. The other main types of glaciers are called ice sheets. Ice sheets exist on a much larger scale, and they happen at high latitudes instead of high elevations. At high latitudes is where the low total annual solar radiation is, or where there is a low total annual solar radiation, meaning they have less sun exposure than in other areas. And so that's why they form in such large sheets. And so it makes these regions great for this ice accumulation. So there are two main types of ice sheets in the world, or not types, two main ice sheets in the world, and these are supported on the two polar-most large land masses. So in the northern hemisphere, we have the Greenland ice sheet, and in the southern hemisphere, we have the Antarctic ice sheet. So you're seeing Greenland ice sheet right here, Antarctic ice sheet right here. So about 18,000 years ago, glacial ice actually covered much more than just Greenland and Antarctica. So many other ice sheets were spreading throughout North America, throughout Europe, and throughout Siberia as well. This time in Earth's history, we call the last glacial maximum. The specific label implies that there were other glacial maximums, as we'll see later in lecture, and in fact, just in the Quaternary period, which is the last 2.6 million years, there have been about 20 to 26 large glacial periods. On an average, they've been happening every 100,000 years. So that's pretty cool. But okay, so let's talk a little bit about the two ice sheets that we have currently. First of all, let's make it clear that the ice that covers much of the Arctic Ocean is not an ice sheet, so it's not a glacial ice. It is sea ice or frozen seawater, but it's not fresh water. It's still salty, it's just frozen, okay? So again, in the Arctic Ocean, where we have a lot of ice that is covering the ocean itself, that is not glacial ice. It's very thin. It only has about 4 meters of thickness at its most. And it is salty. And it doesn't survive for many years. It only survives for a few years for the most part. Okay? In contrast to this ice, glacial ice typically lasts hundreds to thousands of years. So, and it's usually much, much thicker than 4 meters. In fact, 4 meters won't make glacial ice, as we'll see in the coming slides. The Greenland ice sheet extends from latitudes 60 to 80 north, and it occupies about 1.7 million square kilometers, which is about 80% of Greenland. So the ice sheet averages a thickness of 1,500 meters, and in certain places, there's a thickness of 3,000 meters of ice within there. So you're seeing here Greenland. You see that for the most part, the coastal areas are not covered by the ice sheet, but the remaining inner part is. So it occupies about 80% of the landmass of that big island. So in the southern hemisphere, we have the Antarctic ice sheet, and it attains a maximum thickness of 4,300 meters. Again, just for reminding you, about 1,000 meters is about 3,300 feet. So if I say 4,300 meters, that would be a little bit over 13,000 feet, I guess, close to 14,000 feet or so. So again, the Antarctic ice sheet has that maximum thickness, and it covers nearly the entire continent, and also some areas that are not per se within land, I guess. They're covering areas at the Antarctic Sea, as we'll see later on. So the overall area that it covers is 13.9 million square kilometers, so much, much larger than the Greenland ice sheet, which again was 1.7 million square kilometers. So because both the Greenland and the Antarctic ice sheet occupy such huge areas, they are often referred to as continental ice sheets. And their combined areas represent about 10% of the Earth's land area. The topography that is underneath the ice appears not to have been an effect on the presence of the ice sheets for this type of glacier, but it does indeed play a role in controlling the flow of certain parts of that ice sheet. So if there are high topography, say right in the middle of Antarctica, then the flow of certain parts may be radially distributed, meaning glaciers in this area will flow outward like this, glaciers in this area will flow outwards like that. From here, they will flow outward like that. Of course, that might not be the case. Topography won't be the way I described it, but it does have a pretty big role in the direction of flow. And it also has a big role on the different accumulation centers that they may be for these ice sheets. And you'll understand what I mean by accumulation centers in a bit when we talk about the glacier parts or zones. Along portions of the Antarctic coast, glacial ice flows into the adjacent ocean. So this creates features that we call ice shelves. These are very large and relatively flat masses of glacial ice that again will extend seaward from the coast, but they remain attached to the land glacial ice. So as you're seeing kind of in this depicted image, the part right here is an ice shelf that is still attached to the main part of the ice over there, okay? These guys over here are no longer attached, so they're no longer part of the ice shelf. They're going to be icebergs, as some of you have heard that term before. So a little bit more than 80% of the ice in an ice shelf will lie below the surface, so a lot more than above the surface. So it's a little bit more than 80% because of the density differences between the glacial ice and the seawater. Overall, the density of glacial ice is about 0.92 of the density of water, but the density of seawater is greater than that of fresh water. So it makes the glacial ice be a little bit more buoyant on the seawater than on fresh water it would like. So overall, a little bit more than 80% of the ice in an ice shelf will be below the surface. So in coastal areas, the ice actually touches bottom, as this image kind of depicts. So over here, it is touching bottom near the coastal area, and then after a little bit, it kind of detaches from the bottom. In those cases where it does touch the bottom, it is said to be grounded. In deeper waters, as I said, the ice will actually float on top of it. They are typically thicker in their landward side than they are in their seaward side. So this area is going to be thicker than this area, and that's kind of to be expected. And they get replenished from the ice sheet that they are attached to, or from snowfall or refreezing right on top of the glacier. So glaciers do flow, as we will see in a few slides. So overall, a center of accumulation lies landward here. So there is no constantly being replenished to the glacier. That glacier flows seaward, and that is how this glacier continues to have snow, or I guess glacial ice as part of it. As I said a second ago, it can also get ice from the refreezing of snow that falls on top of it. So sometimes if there is snowfall on top of the ice, it can get transformed into glacial ice, and it makes up more of what this ice thickness was in the beginning. But again, the main way is through the replenishing from the continental area to which the ice shelf is attached. So Greenland has very few ice shelves. Antarctica, on the other hand, has many ice shelves, which account for about 1.4 billion square kilometers. The Ross and the Ron Filcher ones are the largest two. So those lie here. I think this one's the Ross ice shelf, and this one is the Ron Filcher one. And then the Ross one is actually the size of Texas alone. So that gives you an idea of how big these ice shelves really are. Some satellite monitoring has shown that some of the ice shelves are unstable and that are starting to actually break apart. So in 2002, an ice shelf on the eastern side of the Antarctic Peninsula, known as Larsen B, which was right here, detached from the ice sheet, and as a result, many icebergs started floating throughout the Weddell Sea. The monitoring predicts that the remnant area of Larsen B will be actually detaching by 2020, and it is suggested that these detachments are caused as a response to climate change.